Section 13.4 is about curvature, and more importantly, it's about the unit normal vector. We're going to write nhat for the unit normal vector. And I'm going to break down what it is here. I just put some notes, I never get sick of writing these things down, what all the letters represent in this context. So r of t is going to be the position. If you take the derivative of r of t, you're going to get the velocity. If you take the magnitude of the velocity, you're going to get the speed. And then I also wrote down the formula for ds, the arc length differential. Let's look at a couple of very simple, motivating, conceptual examples so that we can try to understand what the curvature is and what it's measuring. So the easy way to understand this is to try to think of rate of change with respect to ds. So what I'm imagining is a race car driving around a racetrack, and what we're doing is we're looking at what's happening not as time is changing, but every time the race car travels some distance. I'm imagining 1 meter, but maybe it even needs to be bigger than that depending on how fast the car is going. But the concept here is we're just going to take the path and chop it up into evenly sized intervals, and then we're going to try to examine what happens to capital T, what happens to the unit tangent vector as we take these steps along the path. So that's what I've done here is I've drawn two racetracks. The first racetrack is not a very curvy racetrack. It's kind of a gradual turn. And the second racetrack, it's a pretty sharp turn there. You'd be feeling the G-forces. And each of these, I've put the little red dots evenly spaced out. That's what that means for ds to be a constant. And then what we're going to try to do is look and see what's happening to capital T in both of these two scenarios, and I think that's going to let us understand how to calculate the curvature. Okay, so let's go in and let's draw capital T, and what we're trying to do is understand how capital T is changing. So I'm just going to put the unit tangent vectors at each of these places. Okay, and then here's, I'm going to also put the unit tangent vectors on the curvy one. Okay. All right. I think we can see a difference already. You can see in this first picture here is a unit tangent vector, and here is a unit tangent vector. And they're really not that different, right? One's like straight over flat that way, and the other one just turns a little bit more down. So in this picture right here, T is not changing very much. Okay, but let's look at this picture right here. I mean, even if I just look at like these two adjacent T hats right there, one of them is straight horizontal, and the other one has already gone almost straight vertical just from taking one step forwards. And it's clear why, right? Because if the path is turning more sharply, then for the same step forwards, the unit tangent vector is going to change even more. So in this picture, T hat is changing a lot. Okay, so what this means is the more curvy paths have a larger change in T hat, and the less curvy paths have a smaller change in T hat. So this is doing the job that we want kappa to do. We want kappa to measure how curvy is the path. Okay, so we've done it. We figured out what kappa is. When the magnitude of the rate of change of T hat with respect to the arc length is small, that's a picture like this. That comes from a not curvy path. And when the magnitude of the change in T hat is large, then that comes from a very curvy path. But this, okay, great, right? I mean, now we understand the concept, but it doesn't actually help us solve the problem, because how do you take a derivative with respect to ds? That doesn't make sense. These things are all going to be in t's. Remember, like r of t is going to be something like cosine t, t squared or something. So these have t's in them. They don't have s's in them. How am I going to take these derivatives? So we're going to have to just do a little chain rule with this formula in order to turn it into a derivative that we can calculate. So the definition of this derivative is going to be approximately, kappa is going to be approximately the magnitude of the change in t over the change in s. Okay? And when delta t gets very, very small, as we take the limit, then this approximate will become exactly equal to, and these deltas will turn into d's. Okay, so just a little algebra here. This is also the chain rule. So what I can do is multiply on top and bottom by delta t, and I'll end up with this. Okay, you guys see that? I'm basically just multiplying by 1 here. Okay, so now I end up with this, which is, okay, so now I'm going to break these two up. So here I'm going to get the magnitude of delta big T delta little t times, now this is strange. Remember, I'm going to try to take the limit as delta t goes to 0. And this doesn't really make sense to me to have the delta t's on the top. You remember, like when you calculate anything with respect to time, if you're calculating a rate of change, it's always like miles per hour, right? So the time needs to go in the denominator. So that's fine. I'm just going to do a little invert and multiply to make this thing look a little bit nicer. So I'll put 1 over, and then I'm going to invert that thing right there. So I'll get delta s delta t. Okay. All right. Okay, so we're almost done here with this. Just one more little step. So now I'm just trying to deal with this thing, delta s, delta t. Remember, the definition of arc length is this kind of Pythagorean theorem formula that has the derivatives in all of the places. But that's also the definition of the magnitude of the velocity. And that makes sense. Basically, in our distance equals rate times time reasoning, this right here should be a rate, right? Change in distance divided by change in time, that should give us a rate. And that's exactly what I've written here, right? This thing is the speed. So change in distance divided by change in time should be the speed. So that's what I have right here, 1 over this change in distance divided by change in time. So here we get the final formula. Also, they just like to put this thing in front just because it looks a little bit cleaner. So here's the final answer, 1 over the magnitude of v of t times, I'm going to make this a limit. So now we're going to take a limit as delta t goes to 0. And we get 1 over the magnitude of v of t times the derivative of the unit tangent vector with respect to time. Okay, and that's it. So here is our formula for the curvature. Let's jump in and do some examples, but this is basically bad news bears for us, right? In terms of math students, I've just cooked up a math formula that is going to produce some ugly answers. Remember, big T involves taking some derivatives and then putting a magnitude in the denominator because it's a unit vector. So when I look at this, this just seems like it's going to be a bunch of ugly derivatives to me because this thing right here, big T, that's going to have a square root of something in the denominator. So, you know, there's just going to be a few very special kind of problems where this is going to work out in a relatively simple way. But quite often, even if you pick simple formulas, we're going to end up with some pretty ugly calculations here. So let's do some of the ones that I know come out in a nice way. All right, here we've got this helix. Okay. Oh, I don't want 5 there. I want 4 there. I don't know if anybody can see my 3, 4, 5 triangle coming, but so I've got a kind of helix, right? You guys are familiar with this. It does this kind of corkscrew sort of shape, straight up and down. And what we're going to do is find the curvature. I think we're going to discover that for this curve, this motion in space, the curvature is constant. So let's jump into this and see if we can figure this out. So this is the formula I'm trying to use. 1 over magnitude of v times d big T d little t. So first let's find dr dt. So this is v of t. All right, so I'm just taking some derivatives. Okay, and now also I've got a magnitude right there. So I need a magnitude of this. Okay, so square root. So what am I going to get? 9 sine t, 9 sine squared t plus 9 cos squared t plus 16. So this is going to be, I can factor out the 9 and I'll get sine squared plus cosine squared is 1. Then I'll just have 9 plus 16. So this is the square root of 25. So that's 5. Okay. All right. Thanks, teacher, for making up an easy one. Okay. So what does this mean? This means that capital T is going to be V over magnitude V. Okay, so in our problem, this is going to be, so all I need to do here is take the velocity and divide by its magnitude. Luckily, the magnitude of this velocity was just constant. It's totally possible for you to still have variables left in this, like most of the time you will, but because of this sine squared plus cosine, and because this thing is such a uniform shape as it goes up, this time the magnitude of the velocity is not changing. So I'm going to get negative 3/5 sine t, 3/5 cosine t, 4/5. Okay, now what we need to do next is, the formula is the magnitude of the derivative of capital T. So now I'm going to need to take derivatives of this, and this is the stage that usually could get very ugly, because this 5 right there comes from this, which would usually have t's in it. Okay, I'm overselling this point. You guys get it. So let's keep going. Now the derivative of big T with respect to little t. Okay, some more derivatives. Okay. Whew. All right, so we are almost done. So remember, the formula is the magnitude of d big T d little t. So I need to take the magnitude of this, and then I need to do 1 over the velocity. So I've got that here, 1 over the velocity here. So we're getting pretty close to calculating kappa. Okay, so one more magnitude Pythagorean theorem formula, and here I have the magnitude of d big T d little t. You can see, again, because of all the beauty in this problem, I can factor out a 9 over 25, so this will actually just be 3 over 5. Okay. All right, so here's the final answer. Kappa equals 1 over the magnitude of v of t, which is usually a function, but this time it's a constant, times the magnitude of d big T, d little t, which is also usually a function, but this time it's a constant. So in this problem, the curvature is constant. The curvature isn't changing, and that actually makes sense. You know, when you look at our shape like this, well, I didn't draw it very well. When you look at the shape, okay, let me draw it. Okay. These, if you were in a race car and you were driving around this helix, like there's sometimes parking garages, right? When you drive up to the top of a parking garage, if it got like thinner or something like this, then the turns would start to get sharper, but that doesn't happen for these helix shapes, right? It just always goes around in these like perfectly uniform circles that are just rising up, rising up, rising up, rising up. So it makes sense that when we work out the curvature of this helix, the answer isn't changing because of this kind of uniform nature of its motion. So what do we get here as the final answer? 1 over 5 times 3 over 5. So 3 over 25. Yay, we did it. Kappa. Okay, here's another one of these. This time I think our answer is not going to work out in such a pretty way. This shape is a parabola, okay? So if you just look at the way a parabola looks, you can see that down here at the bottom, it's actually quite curvy, but then maybe somewhere over there on the wall, it's actually not. This path over here is actually not that curvy. So what this means is that parabolas have variable curvature. So unlike the last problem that we did, this one I think there's still going to be a lot of variables left at multiple stages. Let's jump in it and see how far we can get. Okay. All right, so this is r of t, so that means I'm getting v of t is going to be 1 comma t. Okay. Then magnitude v of t is going to be the square root of 1 plus t squared. Okay. Which means capital T hat is going to be v over magnitude v. So I get 1 over the square root of 1 plus t squared, comma, t over the square root of 1 plus t squared. Which, to me, it's just easier to view this as 1 plus t squared to the negative 1/2, and then t times 1 plus t squared to the negative 1/2. Okay. All right, so capital T wasn't so bad, but remember, kappa is 1 over magnitude v. Okay, so that's going to be this, times the magnitude of the derivative of the unit tangent vector. So, this looks like it's going to be a lot, because what that means is I'm going to have to take the derivative of this and then find the magnitude of that. So, looks like we've got our work cut out for us. Let's see how far we can get. All right, so derivatives. Okay, I hope I don't mess this up. I probably made a mistake already. I hope I don't mess it up anymore. So, bring this negative 1/2 out front, and then leave the inside alone, and then minus 1 from the power, and then multiply by the derivative of the inside. So already we're seeing a little bit of cancellation. This 2 right there will cancel with that 2 right there. Okay. Now I've got to do a product rule with this. So I'm going to do the first and the second there. So the derivative of t, the derivative of the first is just 1. So this will be 1 plus t squared to the negative 1/2 power, plus the first times the derivative of the inside. So when I take the derivative of the inside, I'm going to have to bring that 1/2 out front. So I'll make this a negative, then there's that t, and there's the 1/2. And then you leave the inside alone. you subtract 1 from the power, and then you multiply by the derivative of the inside. Okay, so we've got quite an expression here, and you can see this started out with a relatively simple position function. So, you know, be ready for these calculations to kind of carry on, you know. There's a lot going on here. All right, so we've done it. The good news at this stage is that we are done taking derivatives. So this is my tip. If you are done taking derivatives, as soon as you're done taking derivatives, you're no longer going to calculate any rates of change. The reason that I'm not allowed to plug in time 3 at the very beginning is because when you calculate the rate of change of something, if you plugged in a number, then everything would just turn into constants and you just get zeros, right? The rate of change of a constant is just 0. So you have to keep everything as a variable until you're done taking all the derivatives. And once you're done with that, then you can just start plugging in the numbers. Okay, so that's what I'm going to do now. I'm going to go ahead and just plug in the time because I'm done taking derivatives. So I'm going to use vertical line notation, this notation right here. That just means I plugged in t equals 3. Hopefully you've seen that notation before. So I'm going to get this. Oh, these 2's are going to cancel. That 2 right there will cancel with that 2 right there. Sweet. All right, so it will just be negative. Oh, there's a t right there, and I'm plugging in t equals 3. So there's the negative and the t. Now this will be, I'm plugging in t equals 3 right there. Okay, so hopefully you can see on the inside, this will be 10 to the negative 3 halves power. Now all of this right here, all of this right here. So I'm going to have 10 to the negative 1/2 power. Minus, now those are going to cancel right there, so I'll have 3 times 10 to the negative 3 halves power. So now I need to do the magnitude of d big T, d little t at time 3. Boy, that vertical line notation, it's not helping me now. All right, so what am I going to get? A massive square root. So it's going to have to be this first thing here, times 10 to the negative 3 halves power squared plus this thing squared. Right now, this is just a Pythagorean theorem. Okay, couldn't be simpler. I don't know why I wrote this so big. Let me clean this up off camera. I can write this cleaner. Okay, so I just wrote this a little bit cleaner, and then I just used my calculator to simplify these expressions. So I simplified this negative 3. This is, you can see those 2's will cancel right there. So this is basically just 9 times 10 to the negative 3 power. So I got 9 over 1,000. And I simplified this. When you FOIL this out, there's actually a lot of simplifying that happens. And I ended up with 49 over 1,000. Okay. So this is just going to be the square root of 58 over 1,000. And you know, this can simplify, but I'm just going to leave it as a number. The point is, what does Professor Grondel say? That's a number, so that's an answer. So yeah, so now we got d big T, d little t. Also, let's just jump back up here really fast. So magnitude of v at time 3. I think that's pretty easy to see. If I plug this in, I'm going to get the square root of 10. So this is it. We've done it. Yay, hallelujah. Kappa here will be 1 over the magnitude of v, that's the square root of 10, times the magnitude of d big T, d little t, the square root of 58 over 1,000. Yeah, so I mean, I'm sure that simplifies. Looking at it now, actually, that's going to make a perfect square there. But whatever, look. We did it. The point is, these get really ugly really fast. Here's an example where we worked out all the numbers. Please let me know all 500 mistakes that I made when I did this. I'm sure there's arithmetic and algebra and calculus mistakes abound. So let's move on to the next topic. The next topic is the unit normal vector. So what we're trying to do here is come up with a vector that is it's always perpendicular to the path. So we're going to call that capital N, and I want to imagine pool or billiards, you know, the game with a bunch of little balls that roll around on a table. And I'm imagining a billiards ball roll. This is like a top-down view. So we're looking down at the table, and the billiards ball is rolling along the table, and we're going to nudge it in order to change its direction. Remember that capital T has magnitude 1. So if I want both of these to be capital T's, I can only change the direction. Okay, I'm not allowed to change the speed, because if I speed it up or slow it down, then this magnitude would no longer be 1. So let's think about this. You got a pool ball, and it's rolling by, and you're going to nudge it in a way that doesn't change its speed. Okay, let's look at what some possible choices are. So first of all, what happens if we nudged it just straight vertically? That would do what this picture is doing. Right? That will change the direction. However, if I just nudged it straight vertically like that, then the pool ball would already have some horizontal velocity. And then if I added some new vertical velocity in the end, it will actually, I'm producing more velocity there. So that isn't going to work. It's close. But then this new vector that I would produce here, the ball would be rolling faster, right? Because it was already rolling this way, and then when I bumped it that way, now it's going faster because it was already rolling, and then I added some speed. So that's not going to work. All right, what happened if I bumped it straight this way? Well, actually, that wouldn't do this, right? First of all, it wouldn't turn it. Second of all, it would definitely violate this rule, because if the billiards ball was rolling this way and then I bonked it going the other way, then that would slow it down. So that's not going to work. So it's going to have to be somewhere in between there. Okay. So hopefully you can see from this that we're going to have to do some amount of hitting it this way in order to slow it down, and some amount of hitting it this way in order to make it turn. So actually what it turns out is we need to bonk the pool ball perpendicular to the new path. That will slow it down just enough so that the velocity stays constant, constantly equal to 1, but also changes the direction. Okay? So if we want to make a vector that is perpendicular to the new path, this happens when I only change the direction of big T. Okay? Okay, so now we've got this kind of concept. When I imagine a particle traveling through space and turning, I have these two vectors, two unit vectors glued to the particle. I imagine the particle driving along in this direction, and then I imagine a bunch of little like billiards sticks poking as it goes by towards the direction that it's turning, and that's what makes it make a kind of arc. Okay? So what we've done is, actually I shouldn't call these nhats yet, because all I've done is taken the derivative. There's no reason to guarantee that these things are going to be unit vectors. So this is how you can produce a normal vector, right? As it goes by, you just bonk it in the direction perpendicular to where it turns to, and that will change the direction but not change the speed. What we want is but we want to always have unit vectors because we're going to be calculating projections with these. So here we've got it. So taking the derivative of big T is going to produce normal vectors, but I want unit normal vectors. So we've got it. Here's the formula. N hat is going to be the derivative of big T with respect to little t, and that gives us a perpendicular vector. So now all you need to do is just divide by the magnitude of that, and you will get a unit normal vector. So what is it? N hat is a unit vector that's perpendicular to the path. There's two. You can actually see there is another unit vector that points out this way. And the ones that we are calculating, N hat, is always going to be the one that's kind of inside the curve. So if this curve curved back around this way, then the N hats would pop out and be going on the inside like that. So yeah, so there's capital N. Let's do an example where we can calculate one of these things. I think it's actually a little bit shorter and easier than kappa. Okay, so I've given us a curve here. Obviously, this is a circle. And what we're going to do is calculate capital T hat and capital N hat. And I think this is going to make sense just from a conceptual point of view. So let's just run through the calculations here. So big T, well, first let's get, so there's R. So first let's get V of T. Now let's get magnitude V of T. So that's going to be the square root of, this will be 9 sine squared T plus 9 cos squared T. So that's 3. So this means big T hat is equal to, I'm going to do V divided by the magnitude of V. All right, I think it's pretty clear what's going to happen here, right? This 3, when I divide these 3's by that 3, it's going to cancel. So I get big T is negative sine T cos T. Okay, sweet. Now let's do capital N. Okay, so the formula is the derivative of big T divided by the magnitude of the derivative of big T. So negative cos T, negative sine T here. Okay, so brilliant. Now I'm supposed to divide by the magnitude. I think you can see just by looking at this, this magnitude is 1. So N is going to be this vector here divided by 1. So I just get negative cos T, negative sine T. Okay, all right, so let's try to make sense of these negatives. I'm going to hop over to CalcPlot 3D because actually these negatives that are happening right there, that and these two that are happening over here, that's actually pretty reasonable thing. I think we could have predicted search. I think we could have predicted this. So let's look at CalcPlot 3D and see how it comes out. Okay, here I've got CalcPlot 3D, and so far all I've done is get the computer to graph the point. This is just the location of this particle as it moves around. Okay, so let's see. I can have the calculator display all of these different vectors. So I'm going to go here, and I'm going to show the trace vector. So this is the vector that is pointing at the location of the particle. So this is just plotting this vector, positive cosine, positive sine. And you can see how this vector just goes outward from the origin towards the point and is kind of always pointing at where that point is. Okay, now let's get rid of that and show the unit tangent vector here, okay? So you can see the unit tangent vector, instead of pointing directly out to it, okay, remember that we changed the sign of just one of the coordinates. So instead of starting at the origin and going right and up, it starts right here and goes left and up. Remember, because this negative sign right there, okay? So instead of going right and up to get to the point, I'm now going left and up to get to that unit tangent vector. So it makes sense the way these signs are changing. Let's do one more for the unit normal vector, and then I think that one really makes sense. So I'm going to put the unit normal vector on this one. And you can see, okay, this is really doing, oh, I forgot my threes. Let me put the threes in here. There we go. Oh, look at this. I like this even better. Okay, zoom out, buddy. All right, there we go. See, now they're like little tiny. Now they're just like little units, okay? So, did I have threes in the original problem? Yes, I did. Okay. All right, so now this makes sense to me because in order to get to the point, I had to go out and up to get to the point. And then when we did the math and we calculated the unit normal vector, both of the signs ended up negative. You can see the original problem here had a positive cosine and a positive sine. And then after we go through all the math and we end up with a negative cosine and a negative sine, basically all we did was we took the original vector that goes out to the point, okay, and these negatives in front of it just change the sign. Am I over-explaining this? So all we're going to get now is just a smaller vector. That one has magnitude 3. This one has magnitude 1. And it points in exactly the opposite direction. That makes sense because this thing is moving in a circle. So if you're always pointing out at the point, the direction that it's turning in is always pointing right back in towards the origin. Okay. So I think this example really confirms that the math is behaving the way that we want it to, okay? The unit tangent vector always represents the direction of motion, and the unit normal vector always represents the direction of turning. That's good content there. Let me write that down. So here's the conclusion for this. Okay, so that's it. Now you understand the curvature and the unit tangent vector and the unit normal vector. So the homework is posted up on Canvas now. Let me know if you get stuck on any of these problems. From your point of view, the majority of this, the difficulty really isn't going to be understanding the concept. The difficulty is just going to be, keeping track of all this calculus because of the kind of ugly nature of these of doing this process of taking magnitudes and putting them in the denominator and then taking derivatives of that. So just remember, as soon as you're done taking derivatives, then you can go ahead and plug in the time that you're talking about. So let me know if you get stuck on them, and I'll do my best to give you a hint. And I'll see you guys on Tuesday.